Alright, so here we have a problem on drag force, but before I get into the problem, I'm going to go ahead and give a quick explanation of exactly what drag force is. So drag force is a force acting opposite to the motion of an object. Now it's important to realize that drag force is not the same as frictional force. So for example, if we had a box like this, and you were to push it from this side, like this. So this would be the direction of the force which you're pushing it with. This would be the direction of the friction. So if we were to push it like this, if we begin to push that box faster, the friction force would remain the same. However, this is not the same for drag. So when it comes to drag force, what we're doing is we're going through a fluid, like this. Then we would be passing through the fluid, like this. All right? So when we increase our velocity, we are creating increasing turbulence, and this is what sucks away the energy and increases that resistive force. So now I'm going to introduce our drag force equation. So that equation is F equals 1/2 CD rho A V squared. Alright, so I'm going to go ahead and explain how each component of this equation affects the overall drag. So first I'll start with CD. So CD is our drag coefficient. Alright, and it simply quantifies the drag or the resistance of an object. So as this resistance increases, so does our drag force. So it quantifies the resistance of an object. And as it increases, so does our drag force. All right, and then also note that CD is dimensionless. Next, we're going to move on to rho, which is our density. So that's going to be the density of the fluid our object is traveling through. All right, so our drag force is going to increase as our density increases. And I like to think of it as the density is in a way aiding that resistive force. So when you have a denser fluid, the particles of that fluid are packed a lot closer together, which creates more resistance to the movement of the object. So now I'm going to go ahead and describe our area. So this is just going to be the area is the projected cross-sectional area of the body perpendicular to the flow direction. So it's going to be perpendicular to our velocity. So for instance, if this was our object, like this, and our object was traveling this way, so our velocity would be in this direction, then we would be looking at the area of this face. All right, so drag force is going to increase as the area increases. Right? And this is because the larger area provides more surface for the fluid to interact with and resist the movement of the object. And then lastly is just our velocity. So this is just going to be the velocity of the object All right, and the drag force will be proportional to the square of the velocity of the object. So again, as velocity increases, drag force is going to increase. All right, now that I've explained the concept of drag, we can get into our problem. So let me grab that. All right, here is our problem. So our problem is to reduce the drag coefficient and thus to improve the fuel efficiency, the frontal area of a car is to be reduced. We want to determine the amount of fuel and money saved per year as a result of reducing the frontal area from 18 feet squared to 15 feet squared. Assume the car is driven 12,000 miles a year at an average speed of 55 miles per hour. Take the density and price of gasoline to be 50 lbm per feet cubed and $3.10 per gallon, respectively. The density of air is 0.075 lbm per foot cubed. The heating value of the gasoline is 20,000 BTU per lbm, and the overall efficiency of the engine is 30%. Take the drag coefficient as CD equals 0.3. Okay, so what we have is a car. So let me draw that the best that I can. Okay, we have a car, and we're assuming this is the front of the car here. So our thrust and our velocity will be going in this direction, which means our drag force will be going in the opposite direction. All right, so what we want to find is the amount of fuel and money saved per year by reducing the frontal area of the car. So I'm just going to start out by writing our givens. So our original area is 18 feet squared. New area is 15 feet squared. Okay, the distance is going to be 12,000 miles per year. Our velocity is 55 miles per hour. The density of the gas is 50 lbm per feet cubed. The density of the air is 0.075 lbm per foot cubed. Okay, our cost is $3.10 per gallon. Our heating value is 20,000 BTU per lbm. All right, and then our efficiency of the car is 0.3, and our drag coefficient is also 0.3. So to start off, since the area is directly proportional to the drag force and the work done to overcome it, the percent reduction of the frontal area is going to be equal to the percent reduction of fuel consumption and therefore the cost of fuel. So we're going to start by finding the percent reduction, and that's going to be equal to the reduction of the area over the original area. So that's going to look like our original area minus our new area over the original area. And that's going to be 18 feet squared minus 15 feet squared over 18 feet squared. And that's going to give us 0.1667, which is equal to about 16.67%. So that is our percent reduction. Now, in order to determine exactly how many gallons and dollars per year we're going to save, we need to start by finding the drag force for the original area of the car. And again, our equation for drag force is FD equals 1/2 CD rho A V squared. Okay, so the drag force acting on the car before reducing the area is this. we're just going to go ahead and plug in our values. So it's going to be 1/2 times our CD, which is 0.3, times the density, and this is going to be the density of the air, not the gas, because the air is the fluid that our car is moving through. So that's going to be 0.075 lbm per foot cubed. And that's going to be times our original area, which is 18 feet squared. And then times our velocity, 55 miles per hour squared. And then we're going to go ahead and convert that velocity from miles per hour to feet per second. So that's just going to be 1.4667 feet per second over 1 mile per hour. And remember to also square that. And then we're gonna convert this all to lbf. So that's gonna be 1 lbf over 32.2 lbm times foot per second squared. Okay, and calculating that is gonna give us 40.9 lbf. So that is our original drag force. So, why are we reducing the frontal area, and what does this have to do with saving fuel? So, in order to continuously move forward, the car is going to have to overcome this drag force that's acting on it, and this requires work. So, since work is force times distance, we can say that the work required to overcome the drag is just the drag force times the distance the car travels. So our equation is going to be work equals force times distance. And if we want to find the work to overcome the drag force, that's just going to be the drag work is going to be equal to the drag force, which is what we just calculated, times the distance, which we called L. Now, if we plug in our values, our drag work is just going to be equal to our 40.9 lbf times 12,000 miles per year and then we can convert the miles to feet, so that's 5,280 feet for every 1 mile. And then we're gonna convert this to BTU per year. That's what we want our work in, so that it'll be consistent with the heating value later on. So we're just gonna multiply that by 1 BTU per 778.169 lbf times feet. All right, so that's gonna give us a work value of 3.330 times 10 to the 6th BTU per year. Okay, so that is our work required to overcome the drag force. And now, in order to determine the amount of fuel we will need, we need to determine how much energy input is required for this distance of 12,000 miles. Now, how are we going to do that? Well, we know that efficiency is the ratio of output to input energy. So our efficiency is going to be N equals our output over our input. Now, in this case, we've already solved for our output, which is work, so we can use this with the efficiency that we were given to find the required energy input. So our equation is going to look like this. The efficiency of the car is going to be equal to the drag work over the energy input. All right, and since we're solving for energy input, we can rearrange. So our energy input is just going to be the drag work over our efficiency. And that's going to be equal to 3.330 times 10 to the 6th BTU per year over 0.3. And that's going to equal 1.110 times 10 to the 7th BTU per year. So that is our required energy input for the year just due to drag, not overall. So now in order to find the amount of fuel needed to supply this much energy, we need to understand what our heating value actually tells us. So the heating value is the amount of energy released per unit mass of fuel when it is completely burned. Alright, so since this value is per unit mass, if we divide the energy by the heating value, we will get the mass of fuel needed. So we could take this. Our mass of fuel is going to equal the energy input over our heating value, and that's going to be equal to 1.110 times 10 to the 7th BTU per year, which we just calculated, over the given 20,000 BTU per LBM. Alright, so that gives us a value of 555 LBM per year. Okay? So since we want the amount or the volume of fuel needed, now we can just simply divide the mass by the density of the fuel, and that'll give us the amount of fuel. So our amount of fuel equals our M fuel over the density of the fuel or the gas, same thing. So that's going to be equal to 555 LBM per year over 50 LBM per foot cubed. And that's going to be equal to 11.1 foot cubed per year. Okay, and then the cost will just be our amount of fuel times the unit cost that we were given. So our cost is going to equal that 11.1 that we just found, feet cubed per year, times $3.10 per gallon, which means we have to convert our feet cubed to gallons, so 7.480 for gallons per every 1 foot cubed. And calculating that out will give us a cost of $257.4 per year. Okay, so now finally we can take our percent reduction that we found in the beginning and we can multiply it by our original amount and cost to get our amount reduction and cost reduction. Okay, so our amount reduction is just going to be equal to our percent reduction times our original amount. And that's going to equal 0.1667 times 11.10 feet cubed per year times 7.4804 gallons, and that's per every 1 foot cubed. Okay, and that's going to give us 13.84 gallons per year. So that is how many gallons we are saving per year just by reducing the area. And then our cost reduction is just going to be a very similar thing. That's going to be our percent reduction times our original cost, okay, and that's going to be 0.1667 times $257.4 per year, and that is going to give us a value of $42.91 per year. So that is how much we are saving in fuel per year, again, just by reducing the area. So going back to the little diagram that I drew, really what we did is this frontal area right here is what we reduced, and that also reduces the drag, which means that we need less energy input to move the car forward, which means that we need less fuel, which will cost less. So that is exactly what we found down here.